In the real world, we have lots of physical phenomena. There are sites, actually, one just happened in Ohio, where chemical explosions occur, and we have to avoid that space for a certain amount of time. Then what we see is that that explosion can affect an area in a radius. So they're actually saying that in that case, that explosion is affecting further beyond what they thought. It's starting to contaminate different types of areas for animals further out into the real world. So these physical phenomena are these differential equation expressions that represent decay, growth, and cooling. So we're going to look at each of those three types of examples. We're going to look at radioactive decay for Chernobyl. We're going to look at population growth of fruit flies. And then we're going to look at Newton's law of cooling for, I can't remember if I picked the dead body or a pie coming out of the oven. So, but these are actual formulas and methods that people use in order to determine things. So like when it tells you to let your food cool for so many minutes, somebody somewhere calculated how long it took for internal temperatures to get there, and they measured them using these formulas. In many applications, the rate of change of a variable y is directly proportional to that value of y. If y is a function of time, the proportion can be written as follows. So we have a rate of change of y with respect to time proportional to y and some constant k. This is known as like the constant of proportionality. The general solution of this differential equation is modeled by this theorem here. So that's what I've been referencing when I say that our C kind of comes down in front, and C always represents the initial condition. So C is kind of the equivalent of y naught. So sometimes you'll see an equation y equals y naught e to the kt, where y naught represents the initial value. So if there are 3 fruit flies to start, then C or y naught would be 3. If something is growing, then our exponent will be positive. If it's decaying, then our exponent will be negative. A lot of substances out in the world have what we call half-lives. Half-life is the time at which it is safe for people to return. So half-life is the time in which it is safe for people to return. I think there are like a homework question or two where you have to like reference these in your notes. That's kind of why I have them. So in 1986, we saw that there was this radioactive substance in Chernobyl. So what happens is there's this area and people are living there, and these nuclear bombs kind of went off that contained this potassium isotope. And this area became unsafe to live. And what they saw is people who were living there were exposed to this substance. It was absorbed into the ground and the water, and they were becoming sick. So they were becoming like manic and uncontrollable and foaming, and it was just like really gruesome, but not fun. So some scientists did some research, and they decided that there was about 15 grams of this potassium isotope released during the explosion, and it was absorbed into the water. How long will it take for 15 grams to decay to 1 gram in which it will be safer to drink? So that 15 is your initial condition. So that means times 0, the y naught, or the c value, was 15. We want to know the time when y is going to be 1. So we have 0, 15. We're looking for y1. And we go up and we have our equation that is going to involve the k value for half-life. So we can't figure out what we need until we use years as representation of half-life. So if you started with 15, 30 years represents half-life, how many grams are going to be there 30 years later? Yeah, 7.5. So what we're going to do is we're going to take this idea here. 15 is like my C value. But now my Y value is going to be 7.5. My time is 30 years, and we're going to solve for K. So we get K is equal to the natural log of 1/2 over 30. But what do you know about the natural log of 1/2? Well, that's really like the natural log of 1 minus the natural log of 2. And what do you know about the natural log of 1? So if you don't want to have an ln with a half in it, all natural logs of 1/2 are really equal to negative the natural log of 2. Forever and always now. So this K value becomes equal to negative ln 2 all over 30. So if I want to know the time at which it is now safe, my formula has transformed. It's now y equals 15e. I learned what K is. T. So last time we solved for K, this time we're going to solve for T. Because this time again I know Y. 1. What do you know about an e to an ln? They're just going to I have to bring my negative 30 into my exponent because it's like in front of it and has a variable. So like last time when we did them, there's no variable because of your t. You can't do the e's and the ln's canceling until the t is up in the variable. Because this is e to the ln of 2 over negative 30, kind of like times, no, not times, power to a power. I'm gonna make sure this makes sense. Like that. So when you're multiplying, we're not adding this time, we're multiplying them. So when you multiply, it's a power to a power. So the only way for the e's and the ln's to cancel is for my t to be a power of all of that, not multiplied by all of that. I was like, wait, my math does not work. For whatever reason, well, I wrote it like so this is like a power to a power. And again, if you want to treat your constant with that, it makes multiplying easier down the road. So what I like to do is treat that ln of 2 and the negative 30 with like the t. I treat it like, oh, the negative t over 30 is sort of all one grouping being multiplied by the ln of 2. So I'm going to bring it all up as my power. So I have 1 over 15 equals e to the ln of 2 all to the negative 1 over 30 t. Because the e and the ln have to nicely and cleanly cancel each other. So you can't be multiplying anything else. It has to change to a power to a power. Now my e's and ln's cancel, and I get 1 over 15, 2 to the negative 1 over 30t. And ironically enough, I have an e and an ln cancel, but in order to get that exponent down, I have to ln both sides. Anytime you ln where you have a 1 on our fraction, we know it's going to go away. So the natural log of 115 become negative the natural log of 15. So now I can bring that power back down in front. Multiply a negative times a negative to get a positive 30. Divide by ln of 2. These are different divisions because now you're dividing by the ln of 2 and the ln of 15. Those ln's don't cancel. They could, because they're not subtraction turning to division, it's division. And then you get, and then you would take this on your calculator and get a number. And from what I recall, it's a pretty decent sized number. $117.2067. So what that means is from the year 1986, you have to add 117 years before people can return to that area. That's like a real thing. People try to sneak there now, and then they end up getting these. You have to go and like, So that's how we use these with growth and decay. Now, that was when we were given the C value. What happens is sometimes we'll solve these in calculus measures when we won't be given C. So it's just important to kind of have an idea and understanding because right now there's not really a lot of calc to learning. It's sort of just like, hey, you need to know how to do this for the day. All right. Fruit flies. An absent-minded graduate student at a university is studying a population of fruit flies in a biolab. She works under the premise that this experimental population of fruit flies increases according to the law of exponential growth. She counts 100 flies after the second day of the experiment and 300 flies after the fourth day. However, she forgot to report the number of fruit flies she had initially. Approximately how many fruit flies were in the original population? Round to the nearest fly. So on day 2, we have 100. So that would kind of look like 100 equals CE K2. On day 4, we have 300. So that would be 300 equals CEK4. Solve for C in both equations. And if you have two equations solve for the same variable, then you can set those two equations equal, right? So if I had like y equals 3x plus 4 and y equals 7x plus 5, you would then just say 3x plus 4 equals 7x plus 5, solve for x. Same thing here, but we're going to solve for k. So we're going to say, okay, the purple equation, it's like saying C equals 300 divided by EK4. The blue is 100 equals EK2. So then we can say that 300 over EK4 equals 100 over EK2. Cross multiply. Divide by like the 100 and the EK4, so you get 1/3 equals e to the K2 over e to the K4. But again, if two things have like bases, what do I do to their numerators? You subtract. So these are like terms. So you get 1/3 equals e to the negative 2k. How do you get rid of your e? So we get that our k is a natural log of 3 over 2. Now we can take K. What's the time I want to know number of fruit flies? Yeah. So we're going to say that Y equals C E to the natural log of 3 over 2T. And then we want to know when T is 0. And any sort of point we want to use could be used. So we still don't really know our C value, but what did we say over here? We said that C was equal to 300 over EK4, or C was equal to 100 over EK2. And we also know K is ln of 3 over 2. So in order to do this, we have Y equals E to the ln 3 over 2. We plug 0 in for T, but I need a C. And either C, either purple or blue, will work. Does that make sense? What happens is I end up with 100 over E ln 3 over 2 times 2. So my 2's are going to cancel. I'm left with E to the ln of 3, which becomes 3. So this Y equals 100 over 3. E, what do you know about anything times 0? Anything to the 0 power is, so then you get 100 divided by 3, which is 33.3333, but it said to round to the nearest whole number. 33 fruit flies. Became 300 fruit flies in 4 days, and that is when fruit flies are off. After it stops advertising, a manufacturing company notices that its sales have dropped 100,000 units per month to 80,000 units per month. If the sale follows an exponential, aka CE to the KT, pattern of decline, aka decay, what will they be to the nearest unit after another 2 months? So again, you have to take your initial condition, plug it in, and solve. So it said initially they were at 100,000. After 4 months of removing their advertising, it was at 80,000. So that's 0, 100,000, 4, 80,000. Solve for K. So initial condition is 100,000 times 4 is 80,000. So we'll put a 4 and an 80,000 in for T and Y. Solving for K. That leaves you with 8 over 10, which is really 4 over 5. ln n both sides gives you ln 4/5 equals 4k. 4k equals ln 4/5 divided by 4. If it's an exponential pattern, what will they be at after another 2 months? So don't fall for the trap, right? AP or whoever's setting you up to plug t equals 2 in. But it's not t equals 2, it's t equals 6. Because it's 4 months plus 2 additional months. So we want to know the time at 6, how many units they will be at. Again, for your C value, we know the initial condition this time. The initial condition this time is at 100,000. So multiplying by that 1/4 and that T, kind of pull that 1/4 and then, T is 6. Over together here, because they're not part of that ln. So all of this is to the e. You want to make sure that it multiplies out that way as well. We're just going to type that in on the calculator. So it'd be like 100,000 E, and then I would probably put my 6/4 now, ln parentheses 4/5. Hopefully we're going to pause for today.